this work is about accelerating the static analysis of neural networks by what we call batch representation of abstract values. For the general context, as you know, IA is increasingly used in critical embedded systems, and what we would like is to have some safety properties like what we have for usual software. And in this context, we want robustness properties, so we want to prove that small changes in the inputs will not change significantly the outputs. And we want explainability, which means to understand why neural network is giving some answer. So this is the kind of things we are interested in. To obtain these results, we are using abstract interpretation techniques. Why we do that is because since abstract interpretation is formal method, we can have guaranteed results. Another advantage is that we can work on sets of inputs, not on single inputs. We can reason on sets of inputs in a one single analyze, and also we can answer to our question concerning robustness and explainability. In the Numalis is a company which develops software for that, and when we have abstract interpretation tools for these questions. Anyway, there are some disadvantages in these methods. Is that for the abstract interpretation to be precise, we need to use abstract domains which are relational, and this is costly. It is very time-consuming and mostly memory-consuming. The most important bottleneck is the memory, actually. And another disadvantage is that the abstract interpretation does not work with standard values, with floating point values. We have to use these abstract values. And so we cannot use the inference, the interpreters that we have in the libraries like TensorFlow, Pytorch. We have to re-implement our own interpreter which works with abstract value, and this is time-consuming, and we cannot optimize as much as these framework do. Okay, so if we go a little bit into details, what we want to do is to take a neural network, which we can view as a function from Rn to Rm, and some abstract value in the input domain. And we want to compute the smallest convex envelope of the result. So we have one strong requirement, that is that we want to be sound, that is we want to enclose the actual image of a result. We can be over-approximating, but we want to have an enclosure of the exact result. And we also have, so this is a strong requirement, but we also have a weaker requirement, which is about precision. We want to have the smallest possible convex set, obviously that satisfies the soundness condition. This is to minimize the over-approximation. Okay, so this is our problem. In the context of neural networks, if I give some example for a classifier, if we execute, if we do some inference with a standard value, we would obtain the red result, a weight for each class at the end of the network. And instead of using an image, we are going to use a convex hull around this image, for example, by putting one interval for each pixel. And so we will obtain an interval for each class in the output. And in this case, so this is the lower bound and the upper bounds are given in blue. In this case, we can say that we are robust because the lower bound for the dominant class is still higher than the upper bound for the second class. And in addition, what we can obtain is these red points on the image, which say which pixels have contributed the most to the classification. This is what we call an heat map, and it's a way to explain why the answer of a network is what it is. It's because of the red pixels. Okay, so before going into the contribution, I need to introduce some material about affine forms, which are the abstract domain that we're going to use. So there exist many abstract domains when you do abstract interpretation. One of the simplest ones are the interval arithmetic, which graphically correspond to boxes, that is with intervals for x and y. If you are in 2 dimensions, then you can define a rectangle or an hyper-rectangle in n dimensions. And there are many other domains like polyhedra, like octagons. But what we are using here are affine forms and the affine arithmetic, which graphically corresponds to zonotops. Zonotops are forms like this one, which there is a central symmetry around, with the central point of the polytop. And what we can see is that there are relations between variables. For example, this line here corresponds to an affine relation between x and y. So we are more precise. We introduce these relations to be more precise than intervals. Affine forms are very practical for neural networks because they are very precise as long as you have linear computations, and this is the case in most computation in neural networks. Even obviously there are non-linear layers. So from a more mathematical point of view, we can introduce an affine form like that. Let's start with intervals. An interval can be represented by its center and a ray, and it corresponds to the interval c minus r and c plus r, where c is the center and r is the ray. You can see an affine form as a center plus several rays. So there are different sources of approximation that we call noises, and we keep them independent to keep more relation than in a simple interval. So we have a center C, and we have several rays of intensity alpha, and these alpha are values, are the intensity of a noise, and the epsilon I is the noise symbol. It's a formal variable that we just evaluate at the end when we want to compute the concretization, the interval value of the affine form. And this concretization is C minus capital R to C plus capital R, where this capital R is just the sum in absolute value of the intensity of the noises. So we can compute with such affine form. For example, here I have a vector X of 2 affine forms. We have the center 1 and 4, and next we have 3 noise symbol epsilon 1, epsilon 2, and epsilon 3. And then we are going to compute WX plus B. And for example, the new center here 7 is obtained by doing 2 times 1 plus 1 times 4 plus 1. We obtain this 7. And if we watch at the coefficient, the noise, the intensity of the noise of epsilon 1 in the result, it is 2 times epsilon 1 minus epsilon 1. And so here we are going to reduce the noise by this subtraction because we know that both noises are going from the same source epsilon 1. So we obtain these results if we compute the concretization for the first dimension. We have 1 plus 4 plus 1 in absolute values, so it's these terms makes 6. We have 7 minus 6 to 7 plus 6. Okay. Next, we have to work a little bit more for non-linear terms. So if we take a simple non-linear function like this one, x to the square minus x, and we assume that x is between 1 and 2, so in a affine form, x is 1.5 plus 0.5 epsilon 1. If we developed the term x to the square, we obtain some second order terms, 0.25 epsilon 1 to the square. And this is not an affine form. We cannot have squares of noise symbols. So we replace this epsilon 1 to the square by a new symbol epsilon 2. Doing so, we introduce over approximation because we are losing the relation between epsilon 1 and epsilon 2. But anyway, we obtain a new affine form. And if we compute its concretization, we have something which is more precise than what we would have with intervals. Okay, so we're going to use these affine forms for the analysis of neural networks. And here is the point where we obtain very big arrays. You have to see that we are going to associate one noise symbol to each pixel of the input. So if we have, yes, okay. In addition to this, we will have new noise symbols for all the nonlinear computation. So we start with many noise symbols and we introduce many others during the inference, the abstract inference. So even if we affine from a few noise symbols at the beginning, after a few layers, all the noise symbols, because of the combinations, all the affine form will have all the noise symbols. So this is a lot of data. So we also merge some residual, some of the new noise symbols into residual symbols to limit that. So, but it introduces also over approximation, but we limit like this. But we still have many noise symbols. For example, at the beginning, we take the value of a pixel and we generate an affine form whose center is the value of the color and the noise is a percentage of the intensity of the pixel. This is what we do if we want to have a kind of white noise, but in practice we can use more sophisticated noises. Okay, so we have many abstract affine forms like that, and what we want to do is to collapse them to limit, to have a better representation. So instead, if we just write a simple interpreter, each affine form will be represented by a kind of list, or an array, but a data structure which contains the center and all the noise symbols. And we will have to re-implement the addition, all the multiplication by constant, all the functions for these affine forms. And we will not compete with the best implementations that we can find for tensors. So the idea of batch representation is to revert the problem and to put all the centers of the affine forms into what we call a batch, and that will fit into a tensor. Next, all the noise symbol in multidimensional tensor, and also the residual symbol in another tensor. This enables first to use the tensor implementations of the frameworks, and also to do parallel processing. We're going to see that. So what we do, we take our affine form. We have many of them. For example, for an image of size 224 for the height and the width in 3 dimensions, we already have more than 150,000 noise symbols. This product is more than 150,000 symbols. And so what we are going to do is to create a tensor AC for the centers, another multidimensional tensor for the noise symbols, and also for the residual symbols, another tensor. And what we show in the paper is that we can, the affine operation on affine forms, for example, if I have a set S of affine form encoded in a batch, then the affine transformation of this set of affine form can be decomposed and can be computed in function of AC, A epsilon, and AT. We can do this for linear operation, for convolution, and for addition of subtractions. So, doing so, we can just write our abstract operations as tensor operation that can be directly implemented using the libraries. Okay, and this also works for nonlinear operation. It's a little bit more complicated. We have to introduce some intermediary terms. This is described in the paper, but we can compute, for example, here the value of a batch of affine form in function of the batch of the arguments. This also works for other non-linear functions, and some of them are given also in the article. Okay, and using this, we can define an algorithm, which is also described in the paper, to define our abstract inference, our abstract interpreter. And what is important is that most of the real operations are operations on tensors. Okay, so this enables us to obtain good speedups, because we rely on the library, and as we are going to see, we can easily parallelize what we are doing. So the first measure is to compare what we have on a CPU execution and what we have on the GPU execution, and we can see that we have significant speedups. What is interesting here is that there is no effort for the parallelization, because it is just using the parallelization proposed by Pytorch in this case. So we don't work on the parameterization. We just reuse the best parameterization proposed by the library. The work was before was to represent our abstract value in such a way that it can fit into tensors. This is our contribution. And next, the parameterization becomes trivial for us. Okay. And the method so this is data parallelism, but our method also allows to do task parallelism. Since we the computation are independent on the different components of a affine form, then we can create several batches. This is a part of the noise symbols, this is another part of the noise symbols, etc. And we can do task parallelism. We can parallelize the computation of the operation on the abstract values. Here it's done for workers and the schemes. We did several experiments, and what we can see is that we have a rather good efficiency. If we compare, for example, between 1 worker and 4 workers, it's not 4 times faster, but not so far. So we have a good task parallelism. We didn't have a matching to do it, but the task parallelism and the data parallelism that we use are compatible, can be combined, and we could put both kind of parallelism and obtain even better speedups. Okay, so this is another illustration of what we obtained for 2 size of images. It's the execution timing function of a number of workers. It's an overview of the data which are given in the table on the slide before, and we see that we can win a lot of time by parallelizing. Okay, so to conclude, that we'll say that this batch representation, the idea really is to compute differently with the abstract value to make them fit into tensors in order to reuse all the machinery that we have in libraries. It is possible, and it enables to handle larger networks faster. We benefit from many work done by others. Yes, okay. So in practice, the affine form are not the only abstract domain that we use. So this work has to be adapted also to the other abstract domain that are used for the abstract interpretation of the neural networks. The problem of abstract interpretation of neural network is huge in terms of scalability. So there is not one method that can solve all the problems. We also have to use other techniques, for example, to merge symbols cleverly to avoid to have too much over approximation, and also to work on the representation, the memory representation, the data structure to have limit the memory size that we need. Okay, and that's it. Thank you for your attention.
Let's thank the speaker. I think we have time for 1 or maybe 2 questions. Yes, please.
Hey, Matthieu. So, if I understand correctly, when you batch it, you start with the center value for the input batch, and then when you proceed further, do you do anything different in terms of addition of noise variables, or is that still the same, the introduction of noise variables?
It's interesting. For now, it's the same, but I think that we could add over approximation that would reduce this symbol at the same time. And so we could combine the reduction of the number of symbols with the batch representation to have more efficiency at the price of some unprecision. But it is interesting, yeah? No, for now it's the same number of symbols.
More questions? No more questions? Okay, then let's thank the speaker again.
Thank you.